he's one of a number of people that have been working in Gaussian processes, I suppose, since the GP book. But also with Fourier Regression at Microsoft, and a very interesting thesis it was on things, also things like Monte Carlo game tree search as well. But now he's, I'd say, one of the leading people in the area of the expanding area of Bayesian numerics, which is where Gaussian processes are being used as sort of auxiliary models to improve things like optimization, integration, sampling techniques. He's going to give a talk about that later on. But I think something that's very useful, there's like 100 Gaussian processes are so general, but there's 100 different ways, well there's probably infinite different ways to introduce them. So to approximate that infinite different number of ways, we're having two different ways of introducing. So it's not designed to follow on from my talk, it's designed to sort of give a different perspective on Gaussian processes. So over to Philipp.
Thank you. Thanks, Neil. Thanks to all the organizers for inviting me. It's a great pleasure to be here. I'm always very happy to come back to Sheffield. I'm particularly excited about this opportunity to give this talk. In some ways, this is a super exciting opportunity. I think you are the best prepared audience I've had for a talk since my PhD defense. Because much like my PhD committee, you had 1.5 hours to prepare yourself perfectly for this talk just by listening to Neil right before I get to talk to you. So this will be interesting. We'll see how much new stuff I can explain to you. Many things that I'll talk about will be very close to what Neil did, and some things will be quite different. So sometimes I'll move quite quickly because I think that sort of you get to hear the same story again and again, and then I'll slow down again to get to bits where we are slightly different or thinking about things slightly differently from what Neil did. We have to start quite in a similar way to what Neil said, with maybe the sort of the obvious question, and that's why. Why are we here in an event that's called the Gaussian process winter school? Why is this not called the Laplace winter school or the Poisson process winter processes that makes them so important? Why is this? We used to even have this little bell-shaped curve on our. And I think Neil actually gave a very good answer to it. It's not important in nature, or that they are fundamental to nature. In fact, I would argue that nothing in the real world is Gaussian distributed, just like nothing in the real world is a linear function. Gaussians are an abstraction we use to talk about stuff, and they are an abstraction which is interesting because they link linear algebra, which is something that we understand very well mathematically, with inference, which is something that is very important if you want to talk about the real world. So this talk will ever so often have these black slides, which are chances for you to sort of lean back, take a deep breath, and think about what I just said, and then I'll move on to the next part. The first part was the shortest, obviously. Why do Gaussians link inference and linear algebra? Well, because, and I agree with Neil, that the scalar Gaussian distribution is really boring. I'm not going to talk about these bells at all. I'm going to talk about multidimensional Gaussian distributions, which thankfully Neil has already introduced really well, so I don't have to spend much time on them. They're over here just in case you want to look at them over and over again. Why are these distributions important? Because they have a lot of really great algebraic properties. And it boils down basically to the fact that they are exponentials of a quadratic form. Quadratic forms are things that you learned about in your first year at uni or maybe even in high school. And they are sort of very elementary objects in algebra. Out of the fact that Gaussians are exponentials of these quadratic functions follow certain properties. For example, if you multiply two Gaussian distributions, so this Gaussian distribution with this Gaussian distribution, if you just multiply the numbers that these things assign to every point in this space, then out comes a new function which itself has this same quadratic, exponentiated quadratic shape. Why? Because the product of exponentials is the exponential of the sum of the exponents, and the sum of two quadratic functions is just another quadratic function. And well, to actually do this computation, you have to perform some sort of algebraic steps, and you can think about what they actually are. The interesting bit is that they only involve linear algebraic computations. They only involve inverting matrices, multiplying matrices with vectors. Similarly, well, actually not similarly, but the other great property of Gaussians is if you take a Gaussian distribution and now you project this distribution down to a linear subspace under any linear projection. So if you take this two-dimensional distribution, you project it onto this black line, out comes a new distribution, which is, which is itself a distribution, which is again Gaussian. And we can use this property to sort of reconstruct the rules of probabilistic reasoning in the Gaussian language. So in particular, if you take this projection to be axis aligned, then what this property says is that this, if you take this multidimensional distribution over several variables, which is Gaussian, and you only care about the distribution about one of them, one of these two variables, so that's marginalization, that's the sum rule of probability, then this marginal distribution is itself a Gaussian distribution. So Gaussians are closed under one of the two elementary rules of probability, and that's marginalization. This is in fact, actually, this computation is extremely easy. If you have a joint distribution, Gaussian distribution over x and y, and these might both be vectors, of course, they might both be multidimensional objects, then if you only care about your marginal over x, if you marginalize over y, then the new distribution is a Gaussian, whose parameters are literally you just pluck the elements of the covariance, and that's your marginal distribution. As we now all know, infinitely many variables, you just get to really just suck out these subparts. It's also a horrible property in some sense of millions and millions of variables, and they all interact with each other in a. Then when you only reason about, let's say, 3 of these variables, millions of variables which influence this result. So the power of this language, because it allows us to build these very flexible high-dimensional models. Okay, the third of these more basic properties of Gaussian distribution, you dissect through it, you cut through this distribution. Here, the yellow contour, which is again a Gaussian. So that means if you have a joint Gaussian distribution, and then ask about the other variables, out comes a new Gaussian distribution. Operation that Neil has already shown you, and this is this sort of famous. I'll have to introduce it to you. Those of you who haven't worked with them. At the moment, the important bit is that all of this is just linear. We're just mapping these inverses through the vector things that our computers are really good with. Slides, we have constructed the two basic rules of probability and the product rule, marginalization and conditioning. So if all the variables were interested in relationships between variables, then we state of Bayesian inference just by doing linear algebra. Let's say we're performing a little experiment. Imagine you see a point mass, right? So some object to this point mass. You see it accelerating. So you see, but you don't actually get to observe the individual two forces. With Gaussian language, if you like. This is force number 1, force number 2, because you have some prior belief. Charge, they can be positive or negative. You might have a important bit conceptually, philosophically, are Gaussian distributed. It's a language you choose. Elegant linear algebraic reasoning. Just like real world, because it makes things easy to talk about. The world, it's a language we use to describe what's going on. This is, if you take maybe the way that these forces are applied is a certain number for the objects we're looking for of a likelihood that isn't a probability distribution. X2, which is degenerate along this direction. Distribution and likelihood function, because they're both object. To compute it, you have to do some linear algebra, convert them, you multiply them with some vectors, and out comes this posterior distribution in red. What those forces may have been, and your belief about those two forces has become correlated. This is called explaining away, because there are now various possible explanations for the observations you've made. It could be that the first force was quite large, then the second force had to be quite small, or the second force was quite large, then the first force had to be quite small. This is something that happens a lot of Gaussian process regression, that we can do this posterior covariance. Okay, so that's would even be interested in these models in the first place. They have marginalization, conditioning a linear projection lines of a Gaussian language. And to do perform linear computations. So just building matrices, inverting matrices, multiplying matrices with vectors. That's, I think, why we are here and why we are interested in these models. Now the second question is, what can we do with this? And perhaps the fundamentally most important, many interesting questions and applications is regression. So what is regression? Regression is trying to learn variables, a variable x and a variable y, trying to learn a y. Here is, go through it again slowly, or reasonably slowly, to sort of maybe highlight a few slightly different points to what Neil mentioned before. Regression problem, and I've made it such that this is a very simple problem. So let's say we're trying to learn the dynamic response of a robot and we would like to know how it responds, how it accepts the motor that actuates this arm. And what you might get out is currents, and out come various different reasonably linear. This looks reasonably like a linear function. Which goes through all of these points. Why isn't quite linear in the real world? There's some sort of for this. Now, a way to this I mentioned before, as a function of the form f of x is weight plus W2 times x. W2 is a second weight, and x is. Now one way of writing this function, and I'll use this I'll just very quickly get rid of this and just write a much more compact weight vector W, which consists of a bunch of numbers. In this case, there are two numbers, W1 and W2. And then we have what I call a feature vector phi, which consists in this simple case of just a 1 and an x. So it's a function that you hand an x to, and what it returns is a vector, which consists of a 1 at the top and then an x at the bottom. You could also evaluate this function at various points. You could give it several x's, and then what it would give you back is a matrix, a sort of wide and, well, fat and short matrix, which consists of lots of 1s along here, and then lots of little x's along here. Different x's for all the different x's that you enter to the function. Then you could evaluate this function, f of x, as simply multiplying this feature vector to this two-dimensional vector of weights. Here, over here. So this is a way of talking about this function in a linear algebraic way. So we're sort of first casting the problem as linear algebra, then we're using Gaussians as a framework for inference, because Gaussians link this linear formulation to inference. How are we going to do that? Well, we first put a Gaussian prior over those weights. And again, maybe you don't really believe in the Gaussian prior, but nevertheless it gives you a probabilistic formulation with which you can then start to reason about W in the first place. It's very hard to do this in a non-Gaussian way. So this is my prior over the weights W. It's, of course, again, a zero mean Gaussian with an independent prior covariance. So this sigma here is a unit matrix with, actually it's exactly the unit matrix in this particular case. So it's really just the 1. There's no alpha or anything in this particular case. And what you see here is this Gaussian distribution. So in the green shading is the density. This is the first standard deviation, second standard deviation. And I could draw 3 samples from this distribution, much in the way that you described before. Now, what that gives you is it's a model for W, but it's immediately also a model for F, because we've decided we're going to use this particular phi. So after you've chosen this particular way of representing features with 1 and x, because this is now a linear map and Gaussians are closed under linear maps, the distribution over the function values is itself also Gaussian, and it has this form. And to get this distribution, I literally just took this distribution and I just applied the rule that Gaussians are closed under linear maps. That's all. It's really straightforward. So this distribution corresponds to this distribution in function space, if you like. This is a function which maps from x to y. And the marginal distribution at each point is a Gaussian distribution, and also the marginal distribution of any linear map of these input points is a Gaussian distribution. Now, when I make these plots, it seems like it's somewhat arbitrary to choose those 3 points to represent these 3 samples, if you like. In fact, those 3 samples are exactly equivalent to any rotation of this input domain, right? I could just take this axis and just rotate it along this sort of contour line, and it would, the samples would have the exact same probability to be drawn. So they are in some sense equivalent under the prior, which is why I use these animations to sort of give you a slightly different feeling for, a slightly more powerful feeling for what these models represent. So every single frame of this video has the same prior probability. They are all equivalent. Each of these models is just as likely under the prior. Now we'll soon move to more than 2-dimensional models, and then it gets slightly more complicated, because then you can't do these 2D plots anymore, and I'll just show you those plots over there. But they're produced in the exact same way. Then these animations will also not be quite as general anymore, because in 3D, a circle isn't, a 1-dimensional circle isn't so powerful representation anymore, and in 200D it'll be less and less interesting. But I'll still keep doing them just to sort of fix your eyes on the screen, because people like looking at moving things. Okay, so now this is the prior. Let's do inference. All I have to do is to apply the rules of Bayesian inference that I mentioned 3 slides ago, and all I have to do is just linear algebra. If I get to observe the very first data point, this one here, then what happens is this observation, because this is a linear map, corresponds to a rank 1 Gaussian likelihood function in the weight space. And all I have to do is to take this green prior distribution, multiply it with this rank 1 Gaussian likelihood, and because they're both Gaussian, out comes a Gaussian posterior, and that's this red thing over here. Now if I get a few more data points, oh actually by the way, of course, this is now a posterior in weight space, and this posterior in weight space, just in exactly the same way as the prior in weight space corresponded to a prior in the function space corresponds to a posterior in the function space. Now if I get at the second observation, in this case it's this one here, I just get another rank 1 term multiplied in the posterior still Gaussian, and the posterior over the function has changed. I can keep doing this, and eventually I'll have lots and lots and lots of likelihoods, and they don't all sort of uniquely line up to tell me exactly what the correct linear function is, but their product of all of them gives you a posterior distribution over the linear function that might have generated this data set. Does this make sense? There's lots of people nodding. Okay, that's good. So now, by the way, I'm going a little bit off message here because this is not Python code. But this is the code you would write in some language, let's say MATLAB, to produce a plot like this. The reason I have it in here is to show you that this is not a complicated model. This is the entire thing. So what we do is we defined a prior on W. That was this slide. To do that, I had to fix mu and sigma and phi. I had to say what these three objects are. And that's what this code does. It defines a feature function. So f is just a number that I use to define a feature function. Then it defines a feature function. That's an anonymous function in MATLAB. So this is a little bit of ugly MATLAB foo, but you see that it's just a function that is being defined. Then I define a mean vector and a prior covariance. Prior is done. That defines immediately a prior on the functions. And for that, I literally just project these objects, and this involves a little bit of linear algebra in MATLAB. The important thing to notice here is that there are no complicated functions. It's just evaluating a function, multiplying vectors and their transposes, simple things, nothing complicated. There's no optimization going on, there's no sampling. There's actually sampling here, but really, really trivial sampling. Then I get to see the data. So this happens after you've defined the prior, obviously. When you see the data, that gives you observations, so it gives you these feature functions of the points where you made observations. These are called phi x. That gives you a prior mean on these objects you're looking for, the function values at the points that where you made observations. Now you can condition on that, and conditioning on that is just a little bit more of linear algebra. I'm not going to spend much time on this, mostly because you're not supposed to write MATLAB code here, obviously. But you can look at this afterwards. The point is that it's not particularly complicated. So if you come from a machine learning background, you might be used to these sort of packages that do some magical stuff within the black box that you don't have to understand. There's optimization, there's sampling going on, there's hyperparameter choices, feature learning, all sorts of complicated stuff. If you use a Gaussian process or Gaussian regression model, the entire code is very straightforward as long as you only do these very simplistic basic steps. So it's something to really understand. It's not something to just sort of take as a complicated thing you don't have to think about. It's really straightforward. Okay, so now in reality, of course, the functions you're trying to learn don't usually look linear. They look like this, maybe. This is a slightly more realistic data set. It's still one-dimensional because I like making one-dimensional plots. But maybe this describes more of the kind of data set that you might get in a real application. So I don't know what this is supposed to be. You can come up with your own motivation for why you will have a data set like this in 1D. But it's obvious that you don't want to learn a linear function for this, right? Because there's no straight line that goes through even just these error bars reasonably well. So what are we going to do? There's still a function, just as before, and we'll try and sort of cast it into a Gaussian framework or into a linear framework. So how can we turn this problem into a linear description? Well, we use a nonlinear language to just cast this space in such a way that describing a function in this space is a linear problem. And what we do for that is we just change this feature function that we had before, which described a space of linear functions, and use a different language which gives us a space of nonlinear functions. And what do I have to change in this description to get a nonlinear function? Phi, exactly. I have to change the features. So what kind of features might I want to use to get a more expressive model than just this? polynomials. That's a good point. Okay, so for example, I could just, instead of just 1 and x, I could have 1 and x squared, x cubed, x fourth, and so on. What do I have to change in the code? One line. In fact, I only have to change one number. I have to say, instead of just having features which are the powers from 0 to 1, I want powers from 0 to 3. And then what I get is a different set of features. So in the previous plot, well, I can't show you the weights anymore because now there are 4 weights for these 4 features. But I can still show you the plot in the function space. I now have, instead of just 1 true feature functions, constant and linear, I also have a quadratic and a cubic function. And the posterior looks like this. I have not changed anything in the computation other than this very first line in the code. That's the entire change to this model. And it looks quite different from what we had before, obviously. Now, okay, so cubic doesn't seem to be all that good because there's a little kink in here. So let's go to 7th order. So now I have 8 features from 0 to 7. And this is what the prior looks like. It's sort of more bendy and steep. This is what the posterior looks like. Okay, this is better. It gets us closer to the true function. There's really ugly behavior outside here, and this doesn't quite look right. So maybe polynomials aren't so great a feature, because I'm already using 8 features to describe these 19 data points. What might be a different set of features that might work better? You're waiting for lunch?
Radial basis.
Radial basis functions. Okay, I'll get to those in a second. So there's a problem with brainwashing here, that we're all really keen on these radial basis functions. Let's try a few other basis functions first.
Sinusoids?
Sinusoids, good idea. So here are these gray lines you see in the background, these features. These are sines and cosines. These are all the cosines, these are all the sines. Well, not all of them, just 8. The first 8 and the first 8 sines, the first 8 cosines. This is another feature function. I've changed one line in my code. Everything else is exactly the same. This is what the prior looks like. These are now smooth functions, and they wobble up and down. That's quite interesting. They're also all periodic, and that's what the posterior looks like. Slightly better. We could have higher frequencies to get a better description if you wanted to. Different features. What's the space of all features you might want to think of?
Continuous function.
Continuous functions? There's something over here. Any other proposals? It's literally every possible function that maps from this space to a bunch of real numbers, to a real vector. It doesn't have to be continuous. It doesn't have to be differentiable. It doesn't even have to be finite. It can be anything. Literally any function will work. So here's a set of step feature functions. These are not continuous. These are lots of functions which start at +1 when they move to -1. This one has a step here, 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 and so on. I have 16 of those. This is the code I used to produce this. This is the line I've replaced in the MATLAB code I've shown you before. This is what the posterior looks like. Okay, it looks a bit crazy, right? But in many ways, it's actually better than the sinusoids before. It's really good with this step in here. It also has very interesting behavior over here and over here, if you like. That's one way of using step functions. Here's a different set of step functions. These are step functions which start at 0, and then they move to +1. So over here, there's a 0. These are all 0 over here. So this is one of these non-stationary models that Neil mentioned before. This model says over here the function value has to be 0. I know it has to be 0. And then it just keeps on growing because I have more and more and more features being switched on as I go further to the right. This is what the posterior looks like for this set of features. Slightly different, and obviously it has to go back to 0 over here. Yet another set of feature functions are piecewise linear functions. So they all come in from over here, and then they have at various different points, they have a step where they sort of move up again. So these are all little V-shaped functions. This is what the posterior looks like. These are, now we're going slightly crazy, these are Legendre polynomials. They're only defined on a finite space. In this case, I've scaled it from -8 to +8. This is what they look like. They are all continuous, differentiable, they're smooth functions, but they're defined on this box, and this is what the posterior looks like. We have some other ones. Oh yes, I have little Eiffel towers. So these are exponentiated absolute values. Someone told me that the logarithm of the Eiffel Tower is a triangle. I'm not sure whether this is true or not, but if it's true, then this is Eiffel Tower regression. Okay, this is a set of features. This is what the posterior looks like. And yes, because someone asked about it, here are radial basis functions. Bunch of radial basis functions. if you multiply them, if you add them together, this is what your posterior looks like. The reason I'm showing all these plots is to really drill home the fact that there's nothing magical about these radial basis functions. You get to choose your features. And there's really, try it out. Try any old function that you like to describe your data set that you care about. Okay? By the way, of course, there's nothing about the fact that this is a one-dimensional real line that goes in here as an input. Because the feature functions mask the effect of x. They just take in x and they return a real vector. So what x is can be very general. For example, it could be a two-dimensional vector space, and then I can put my radial basis functions in my two-dimensional vector space, and then I get a two-dimensional prior over two-dimensional functions. So that's a multi-dimensional input, one-dimensional output. I could also have a one-dimensional input space along here, let's call that t, time, and then a two-dimensional output space, x, y1, y2. And along both of these spaces, I could put radial basis functions or any other feature function that you like. What I get is a joint distribution over a bunch of real numbers, which is Gaussian, and I can draw from that distribution. If I would draw from it, what I would get is some kind of curve in this three-dimensional space that moves around in a reasonably smooth way. And if I turned this block around and looked at it from the top, basically, what I would get is really a curve in the two-dimensional space that moves around. So you can use a Gaussian regression model to learn curves. It doesn't have to be just functions. In fact, this input domain doesn't even have to be a real vector space. For example, it could be the space of all strings, and then the features could be n-gram counts over those strings. Or it could be the space of all graphs, and you could define features on graphs, like their order and the number of connections and things like that. That would give you a model that you can use for the regression on graphs. Okay, so that was part 2. Part 1 was realizing that we use Gaussians because they map linear algebra to inference. Part 2 was we can use non-linear feature functions, or just feature functions, together with those linear weights and a Gaussian prior over them, to do regression on non-linear functions, even curves. Multidimensional inputs, multidimensional outputs. Okay, what's the time? Good. So the next step is going to be that we're sort of fed up already with these finitely many features. Because what you've noticed here is that as I went through this set of possible features, it's sort of nice to look at all of them, but you get a little bit sort of wary of all these features, right? Once you realize how large the space of possible features is, you start to wonder how you should ever do inference in this space. So you had a question before, after Neil's talk, how do I choose these features? How do I optimize in the feature space? And there's a huge problem here. Of course, you can use various ways of trying to find good features that describe this function well, of course. And of course, there are ways of doing this. Neural networks is one of them. But there's no way to parameterize the space of all features. Why? Because it's infinite dimensional, and in each dimension there are uncountably many such features. It's not even clear how to parameterize the space of all features, at least to me. Especially since it includes non-differentiable and discontinuous functions. It's really, really a huge space. So how are we going to choose these features? And how are we going to, let's say we have a budget of 16 features, how are we going to choose those 16 features? Well, one interesting way that at least at first seems like it's a way out of this, but it will turn out to be only half a way out of this, is to realize that if you look at this posterior distribution, and by now I actually have to point out this form to you, and so far I've always sort of just waved it away, this linear computation that we have to do, then you notice that the posterior over function values have the following form. It's a Gaussian distribution over the function values at some point little x, which I might be interested in. And that prediction is you take the data set that you observe, the y's, these are the outputs of the function at locations where you got to observe function values. You check for what you would have predicted under the prior for the function value at this point. For that you have to evaluate the feature function at all the input locations, I call those capital X, multiplied by the prior mean. That is your best prediction under the prior mean for what you're going to observe. So this object here is some kind of, it's a residual. It's a difference between what you were expecting and what you got to see. Now, how far did you expect this y to be away from this mean? Right, you have to have a prior scale for what kind of variances you were expecting, and that prior scale is this object here. That's this Gram matrix of sort of prior covariance over function values. What this is an inner product between the feature vectors at the points where you got to observe function values plus some noise, inverted. So this object here in the back, this is some kind of scaled residual. It's a degree of surprise. How different are the observations from what we expected them to be? And then this thing up here is a map that tells you here are some things that you got to see, function values. What do those have to do with the function values you're really interested in, the ones at little x? And that's this covariance here. That's the covariance between the function value at capital X and the function value at little x. And then you add the prior mean, just because otherwise it's missing. Okay, to get the posterior uncertainty, we take how uncertain we were before we got to see function values. That's the prior covariance over the function values at little x. Then we measure again how much information in some sense was contained in the objects that we got to see. That's again this scale matrix. This is somehow related to the entropy of the Gaussian observations that we make. And you scale them again by what they tell you about the thing you're really interested in, the covariance between the stuff you got to see and the stuff you're interested in. Now if you look at this expression, the first thing you notice is there's no lonely phi in here. There's no single plus feature function anywhere. All the feature functions are contained in inner products. Inner products of two forms. The first one is this one over here. So this is some kind of mean prediction for function values, and this is often called the mean function. And this in fact can be really anything, simply because shifting a Gaussian around in the output domain doesn't change the fact that it's still a Gaussian. And the second object, which is slightly more interesting, are these inner products between feature functions, basically scaled by the prior covariance sigma. And all we need to do is to evaluate these inner products to get a Gaussian posterior. So if this is, by the way, of course, this is called the kernel, and you will hear more and more and more about it over the next 3 days. Now, if we increase the number of features in here, then we get an ever larger inner product between feature values, but the shape of this the size of this output does not change. So this summation is contained in here. The number of feature functions is contained in this expression. So if I increase the number of feature functions, I'd have to do an ever larger and larger computation within this object. And if I increase it to infinity, I'll eventually have to do an infinitely large summation over objects in this inner product. So to really just n here we go. This object, let's make it easy for ourselves and say this is just a unit matrix times a scalar maybe. No, alpha is alpha times a big sum over all these feature functions. So if I increase the number of feature functions if I increase I, well, the index set here, maybe let's say up to capital N of those, or a capital F. If I increase F to ever more numbers, then this sum gets ever more complicated to do, because there are more and more terms in it to sum over. So that sounds like this is a really challenging thing to do, to have more and more features in. But as you all know from high school, there are some sums which are particularly easy and get easier as their number of the terms in them increases. And those are called integrals. In some cases, very large sums actually get very easy in the limit to infinity because there is structure in them. And we're going to use this trick, which is sometimes called the kernel trick, to find infinite dimensional representations of functions with infinitely many features. So now, first of all, let's look at this code again. If I wanted to rephrase this code in terms of kernels and mean functions, then what I have to do is I have to change a few lines. And you can look at this, at those slides sometime later and just have a sort of get a feeling for where they are. But what's happened now is I've got rid of all the feature functions except for up here. And I've rephrased all the computations further down in terms of these inner products. Here's this kernel function, or covariance function, which is an inner product between feature functions. And here's a prior mean, which I've set to 0. Now, if I can change this expression into something else which represents an infinite dimensional sum, then we've gained something. And now, well, so this is conveniently, I've chosen the exact same example as Neil did before. You will just get to hear it again, and we'll see how much of it you still remember. We're going to do this particular integral limit for the case of radial basis functions. But it's just one example. I'm not saying this is the only feature function for which this works. How am I going to do this? Well, as before, essentially it's exactly the same computation that knew this. So I'm going to go through it relatively quickly. I just have slightly different parameterizations. So, first of all, to make things simple, we pretend that our prior features are independent of each other. So the prior covariance sigma is just a unit matrix times some constant. And I've chosen this constant particularly conveniently that a lot of things cancel out in the end. That prior covariance is some scale times the size of the input domain. So that's the distance between the right end and the left end of the domain that we're going to do inference on, divided by the number of features. So what this is essentially a density of features, right? It's the size of the space divided by the number of features. Then if I do this, then this inner product that we need, this kernel value that we need to evaluate, is this inner product between feature functions with sigma, because sigma is a unit matrix, things get really easy. We have this expression which is essentially the same as over here, just with a slightly more complicated constant in front. That's general for every set of feature functions. Now, if those feature functions are these radial basis functions, these Gaussian functions, then I can write, well, this feature function like this. That's exactly what it is. And this inner product turns into just this big expression, and what it involves is a product of two radial basis functions. And these radial basis functions are Gaussian functions. Now the product of two Gaussian functions is another Gaussian function, which this is something we've now used like 10 times already. So I just get to rephrase this in terms of two new Gaussian terms. So this is a term which does not involve the location of the features. These locations are called CL. This therefore goes outside the sum. And another term which does involve the CL, which is inside the sum. Thank you, sorry. So now I'll let this number of terms in this sum go to infinity in a particular way. I'll do it such that the density of features stays homogeneous over the input domain. So we'll have more and more and more features, but they're still on a sort of a regular grid across the input domain. So we started out with, let's say, 3 feature functions. Now I'll just add more in such a way, and they're all sort of the same shape, such that, I'm not really good at drawing this stays sort of a uniformly distributed sort of space of features. If I do that, then eventually, in every single sort of infinitesimally small compartment of this input domain, I'll have a large number of features which all sort of essentially have the same center C, because it's an infinitesimally small part, right? Sort of location C. So to sum over all of these infinitely many points, I have to sum over in an infinitesimal volume element dc over the feature function value at this point, and that's an integral from lower bound to upper bound. Now I can take those lower and upper bounds to go to infinity as well. And then this just becomes the integral over a Gaussian, which is a well-known number. It's the square root of 2 pi times some parameter numbers. This is down here. And what we're left with is this kernel, which is now an infinite sum over infinitely many features which are uniformly distributed across this input domain. And they are all of this Gaussian shape. So this is a trick for evaluating this infinite sum in a finite computation. And it only works because this converges to an integral. So let's see what this looks like in terms of colorful pictures. Here we've got 8 such feature functions, RBF feature functions. As I increase their number, they become denser and denser, and the shape of this posterior sort of changes ever and ever less. Eventually we get to this limit process where we have infinitely many features functions essentially, and this is the covariance. This is the prior distribution over those function values, which you can still evaluate because you get to replace this finite sum or infinite sum with an integral. And you can actually draw from these distributions, at least on a finite grid, of course. So the trick in all of these plots, of course, is that there are not infinitely many locations on this axis. I've discretized them to use, I think, 120. You just don't see them because your eyes sort of make smooth lines out of these points. Okay. Now, if you do this, this is a neat thing to do, and you notice that you can do it algebraically. But now, of course, you will wonder, this is what the posterior looks like, by the way. Now you'll wonder, what have we just done mathematically? This sounds really weird. Why are we allowed to do this? And the first thing you do is you look up a book on these kind of concepts, and you notice that this is actually a very well-known concept. This has been around for a lot longer than we've been meeting to talk about Gaussian processes for machine learning. These objects, these covariance functions which return positive semi-definite matrices if you evaluate them on sort of blocks of input domains, these are called Mercer kernels. These are functions of two inputs from the same space, such that for any finite collection of these input locations, if you evaluate this function on sort of an outer product of input locations, you get out a matrix which is positive semi-definite. So it's a matrix which is symmetric and has only positive, including 0, real eigenvalues. It's also a matrix which, if you map, just for those of you for whom it's been a while since your linear algebra class, a positive semi-definite matrix is a matrix that you cannot see this, so I'm making this, such that for any real-valued vector v, actually for any complex value, but let's keep it simple, this quadratic matrix gives, in a quadratic form, a number which is larger or equal to 0. If you have this property for any v, this is called positive semi-definite. It's a generalization of a square for real numbers. And in fact, what these things are a generalization of these matrices to infinitely large matrices in some sense. I think you will hear more about this from Nicolas later on today. I could give a 1.5-hour lecture just about these things. So they're really interesting objects. And they've been studied for a very long time, much, much longer than we've been talking about Gaussian processes. Not necessarily much longer than anyone has been talking about Gaussian processes, but longer than we've been talking about them. One interesting observation is that any function which I can derive in the way that I just did, any function which I can derive in terms of an infinite sort of integral limit of an inner product between feature functions, any such function has the property that it is a kernel. So that's a directional statement. If you can write this sort of expression for a function as an integral or an infinite sum or even a finite sum, then you're dealing with a kernel. If then. And here's a little proof for it if you're interested. Okay, so I did this now for the radial basis functions. But as I said, this is not the only space of objects for which we can do that. Oh, first of all, of course, I have to also mention that now what we're doing essentially is we're dealing with an infinite dimensional distribution. Now we're talking about a prior distribution over infinitely many weights. And that sounds really weird. Are we allowed to talk about infinitely many objects? So what a mathematician does if he has to deal with this kind of thing is he just invents a name for it. He says this infinite dimensional distribution is called a Gaussian process. Actually, I'm not even sure whether it's an infinite dimensional distribution. It's a thing. It's sort of a way of writing down a computation which says there is this object that I don't even want to really talk about, which is some kind of, which I'll just give a name to. I'll call it a Gaussian process. And it's a rule that says if you take a finite input domain and evaluate this mean function and covariance function on those finite dimensional subspaces, out comes a Gaussian distribution. Now you can ask, is this enough to define this object? Turns out it is, but it's really non-trivial to see this. There was a question.
That if then? Is that if earlier?
I think not. Might come up with some examples. Okay, so I said we can do this for the radial basis functions, but just to drill home the point that the radial basis function kernel, the RBF kernel or square exponential kernel, is not the only kernel you could use. Here is a construction for the different features that we've mentioned before. So remember those step functions which started at 0 and then moved to +1? So there are 1, 2, 3, 4 here. I could have more of those feature functions. Here are now 20, and here are 100 of them. Little step functions that get ever lower. And you see that this thing kind of converges to something which has interesting regularity properties. It turns out you can do this integral, so you can actually do this limit step to infinitely many little step functions in here, and out comes a very interesting Gaussian process, which is called the Wiener process. It's something you might have heard about before. It's an interesting process. I'm sure Simo will mention it again in his talk on Thursday. It's interesting for various reasons. One of them is that this is what is called a Gauss-Markov process. So if you get to evaluate this function at various points, then to do inference on the posterior, you don't have to actually look at all the data points. You only have to look at a subset, in this case only at the nearest neighbors of the observations. And this is why you can build very fast inference algorithms in this domain. The Kalman filter is an example of that. It's also the reason why the Kalman filter gives you this kind of odd square root shaped uncertainty in the posterior because of this generative process. Well, it's one way of thinking about where they come from. You remember these other step functions that I mentioned before? They don't start at 0 and go to 1. They start at +1 and then go to -1. These are slightly different step functions. I can also increase the number of these step functions to more and more and more. And eventually you get some kind of regular, not smooth, but regular process that has the same structure everywhere. And you can do this integral. Out comes an interesting process which gives you straight lines in between observations. This is called the linear spline model. And many of you will have heard about this in high school. So linear splines can be described as a Gaussian process regression model.
Well, pointing out there that they only give you straight lines on the posterior mean, and I think that's
yeah. Oh, yes. So I could, in my backup I have a slide about this. I'm not sure we have time to talk about this. But the draws from this GP are not straight lines at all. In fact, they have a very, very different property. They are non-differentiable almost everywhere, but they are continuous. There's an interesting property here. The statement, for those of you who know about this, to keep in mind is draws from a GP are not elements of the RKHS, while the posterior mean is an element of the RKHS. For those of you who don't know what this means, just forget about it. Okay. You remember those straight line features? So they come from here and then they have these steps. If you increase the number of them, you get interesting functions which look a little bit more sort of regular than the ones we've seen on the previous slide. And in fact, they turn out to be differentiable once, differentiable almost everywhere. This is what this prior looks like if you do the limit process. These are called cubic splines. And you will have heard about them in high school. And if you do computer graphics, you know all about Bezier curves and cubic splines. And in fact, you can generalize this process that I've just done for piecewise constant and piecewise linear functions to piecewise polynomial functions to get higher order splines. This also works for polynomials. So this is a slightly more boring case. If you have infinitely many polynomials, you just get a series conversions. Now it's not an integral, it's just an infinite series. This is what your prior looks like. This is the posterior. It's a pretty boring posterior if you ask me, but it's maybe just an interesting observation that you can do this on discrete spaces, countable spaces as well. There's also one version of this for periodical features. So now we have some kind of a Fourier basis, again, with a converging series limit that gives you this kind of posterior. Do I have one more? Oh yeah, here's a crazy example. You could wonder if you look at this kind of data set before, how powerful are these methods? How do I have to define my features such that they become sort of universal, that I can learn any function with them? And one naive thing you might want to try is to say, well, let's have feature functions which only cover a certain part of the input domain. Little hat functions that look like this, right? Independent of each other. So those functions allow you to say, well, the function value over here is this, and the function value over here is this, and they have nothing to do with each other. So I can learn very powerful, sort of very general sets of models. It turns out that's not a good idea to try this, because if you do the limit of this, if you just add more and more features and go to a limit statement, what you essentially get is a Dirac delta covariance function, and this is sometimes called the white noise process. It's in quotation marks because it's a bit of a dangerous object. People argue about whether it actually exists or not, because the Dirac delta is this weird object. And what happens if you have this kind of prior, you can't see any structure in here. I've drawn lines, which is a bit silly, because these are really just independent points. It's Cantor dust of just independent function values. If you now get to see certain function values, your posterior looks exactly like the prior, because those function values only tell you something about function values at one zero measure location, or at 20 locations of measure 0. So there's nothing to learn here. So that's not a good idea to use these step functions to model nonlinear functions. Okay, those were parts 1, 2, 3. Gaussian's map, linear algebra, and inference. You can use feature models to do regression, to build a language to describe functions. In fact, it's possible to use infinitely many features if you can represent inner products as integrals. That's called a Gaussian process or non-parametric regression algorithm, and it essentially has infinite degrees of freedom. Now, if you do this, you'll start thinking about, well, okay, you've just noticed that going through this list that there are all these different kernels. There isn't just the RBF, the exponential kernel. There are a few more as well. There's splines and linear cubic splines, and there's polynomials and periodical functions. What is the space of all kernels? Now that's a slightly more interesting question than the one I had before about the space of all feature functions. So the space of all feature functions is essentially just any function. You take any function that maps from the right space to the right space. The structure is completely arbitrary. You get out a Gaussian regression model. Now, by sort of getting rid of an explicit feature representation, by replacing these inner products with kernels, we've made it a bit dangerous for us in a way. We've now allowed ourselves to write down these functions, kernels. I keep leaving this pen over there, which are sort of functions of this form. And now we could ask, are we allowed to use any such function to build a Gaussian process model? And no, we're not. Because what we need to ensure is this property that if you evaluate this function at some kind of outer set of input locations, so then you get out a quadratic, sorry, if these are the same, then you get out a quadratic matrix, this matrix has to be positive semi-definite. So now we could ask, what is the space of functions that gives us this positive semi-definite object? Now I don't have enough time to talk about the actual structure of this space, and I think maybe Nicolas will talk about it a little bit more. Where is he, by the way? Ah, there. Are you nodding or are you shaking your head? Oh, good. Okay, good. But what we can ask already is sort of, can we get a little bit of algebraic structure on this space? Can we get a bit of a feeling for how we can design these functions to use them in regression? And it turns out that some of these algebraic properties are actually really straightforward to see. Here's a simple example. If you take a positive semi-definite matrix and you multiply it by a positive number, a scalar, then this property that this object is always larger or equal to 0, of course, remains, right? So that means we can take any kernel function, any covariance function, any Mercer kernel, and multiply it by an arbitrary positive real number, and we'll still have a Gaussian process model that we can use to do regression with. What does this mean in terms of our Gaussian process models? Well, here is a square exponential kernel Gaussian process prior, which has a sort of implicit 1 in front of the kernel. Now I can just change this here. Up here it is. That's what this kernel function is. Kernel functions are simple, straightforward functions. They can often be written just in one line. If I place this 1 in front, which has this posterior, with a 10, then what happened is the variance of the function values at each scalar input location, each individual location on the input domain, has just been scaled by a factor of, oh sorry, I multiplied by 10 squared by 100, so this has just been scaled by a factor of 10. So this line, which used to be at plus 2, because I'm plotting 2 standard deviations, is now at plus 20. And actually those wobbly lines you see here are the exact same lines that were on the slide 2 slides ago. They're now just scaled up by a factor of 10. And that's the posterior. It looks slightly different though, right? So there's clearly this number is important. So if you thought you could just choose any old kernel, it'll work, I've just added one more headache. Now you have to worry about the scale in front of it. That's one of them. Another thing we can do is, if we have a kernel that we can write in this kind of form, then an obvious thing to note is that if I took these, so this is this weird form that I've written out here is this idea of some finite or infinite sum over locations of feature functions. Then I could take any feature function, these are some feature functions eta, I might take some other feature functions, let's say phi, and just apply them to the inputs before I apply those outputs to the features. And I can do this for any old feature function, and this expression would still be an integral or sum over feature functions, right? It's just a new feature function. So that means I can take the inputs to a Gaussian process regression model and scale them in more or less any arbitrary way, and it'll still be a Gaussian process regression model. So here is a simple example of that. Here's my square exponential radial basis functions Gaussian process model, where I've taken the inputs, and before I applied them to the actual regression model, I scaled them by 1/5. So I just made them smaller. And what you notice is the difference between this plot and this plot is these functions are more regular. They're just smoother. Why? Because I've just taken them and scaled them out by a factor of 5. And the posterior is a much smoother kind of object now. Yes, question?
Can you scale that to, say, like periodic domains? But
Well, I'll get to that in a second. So this is still a very simple thing. I just scaled everything by 5. I could also scale it the other way around by 1 over 2. So I just made them half as wide. So now you get, so this gray line just became steeper. Now we have the similar kind of functions, but now they're more squished together, right? So this is our much more wildly varying model of functions. And this is what the posterior looks like. It's quite different from this line, right? This is called a length scale. Niels already mentioned it. So here's a second headache for you in choosing your kernel. You have to get the length scale right. Otherwise, you'll either get a curve like this or a curve like this, which is maybe not exactly what you're looking for.
Are those pies just for scaling then? Or
No.
some other function?
So, for example, I could choose a quadratic function. There's a very simple next step. Instead of doing a linear scaling, I just do a quadratic scaling. And now, while essentially applying a different length scale to each location on the input domain. Over here, I'll get smooth functions. Over here, I'll get wildly wiggling functions. And the posterior will be sort of more flexible over here than over here. This sounds like a really powerful idea, and in fact it is, but it's maybe almost too powerful to take serious. Why? Because you have to be really careful what you do when you apply this nonlinear scaling to your inputs. In particular, if you choose this function to be non-monotonic, what could happen is that you essentially map input locations from over there back to somewhere here. And now things aren't just Euclidean close to each other anymore as you like to think of them. And you could get models where the function value over here influences your prediction over here, but doesn't influence your prediction over here. Typically, that's not what you want, but you're exactly right. Sometimes you do want it. For example, if you know that your function is periodical, then you could have a periodic rescaling of the input domain, so that everything in here and everything in here and everything in here are essentially the same inputs. And sort of, if you take the input domain and just shift it by 2 pi, you get the exact same location back. What that gives you is a prior that gives you periodic functions and also a periodic posterior. Okay, this case is a silly thing to do because this is not a periodic function. But of course, there are meaningful settings, in particular in technical applications, where you do have periodical behavior in functions. Anything that goes through time might have some periodical properties. Okay. Those are the sort of the 3 things, or the 2 things I can do to a kernel just in terms of the inputs. I can scale the input, I can scale the output, and retain a kernel.
So just going back, I think that's a really nice illustration of something that people sometimes don't follow. Just because you've got a powerful method here, look at his error bars there. Because his prior is wrong. The error bars don't cover the data at all. And people misunderstand that. Error bars, if your model is wrong, the error bars in your model don't cover the data in the correct way when you've got the wrong model. And people misunderstand that about Bayesian inference and non-parametric models, but it's a big issue. That illustrates it really well. A stupid prior, stupid model.
Yeah. And the way to see this algebraically is, sorry that I have to run back through my slides, is the posterior distribution over this GP. Where's my code? Lots and lots of slides. Here we go. This is the posterior distribution. Notice that the posterior covariance, which gives us these error bars, does not contain y. There's nothing in here that checks whether the data points even match up with what we predicted. That's a property of Gaussian distributions. It's another one of the downsides of using Gaussian algebra to do inference. So to rectify this, you essentially have to step outside of this linear regime and reason about, in a nonlinear way, about whether you've chosen the right features. And over the next 2 afternoons, I'm sure you'll get to do this. And it'll turn out to be much more of a pain than just this simple linear algebra. Because you have to essentially run a nonlinear optimizer or some kind of nonlinear optimization on your problem. Okay, so we can scale the inputs, we can scale the outputs of kernels in certain ways and retain Gaussian process models. What you can also do is, if you take a kernel matrix, or a positive semi-definite matrix, and add another positive semi-definite matrix to it, then of course the resulting sum of those 2 positive numbers is still a positive number if you multiply any vector from the left or right and right. So if we add kernel functions together, we get a new kernel function out, a new covariance function out. One way of doing this, here's an example of what I do here, is I've just taken a square exponential with a long length scale and a large variance. signal variance, and a square exponential with a short length scale and a small signal variance. And what you see is the prior has these kind of, it's locally quite sort of flexible, but only on a certain scale, while globally these are relatively sort of regular functions which move on a large scale. So what this allows you to do is to say, well, I'm expecting sort of local fluctuations, but the overall shape of the function is relatively regular. One way of thinking about this is what kernel functions or covariance functions define is some kind of measure of similarity, but I'm moving my hands around while I do that because there's a problem with this, because covariances can be negative. And a strong negative covariance means that the function values are closely related to each other, but they are very different. So this notion of a measure of similarity is a little bit dangerous, but it's sort of true that if the absolute value of the covariance function between two input locations is large, then this tells you a lot of information, sort of lots of connection between two function values or two input locations, while if the covariance value is small, if it's close to 0, then they're sort of almost independent. In that sense, because the sum of two large numbers is large, and the sum of a large number and a small number is also large, you can think of this kind of adding process as a logical OR operation. What this model is saying is two function values are similar if they are measured as similar under either the first kernel or the second kernel in the sum. So this is a way of building models in which you sort of think that there are two processes acting which are independent of each other in some sense. A particular example of that is, and this is where we get back to the discussion we had after Neil's talk before the coffee break, is you can use this to combine parametric and non-parametric models. You could say my kernel, my covariance function, is a sum between an actual inner product, an explicitly written phi transpose phi object, and a non-parametric covariance function, which I only write as a kernel k. Here's an example of that. Here I've added a square exponential kernel to an explicit polynomial feature model with 3 polynomial features: constant, linear, and quadratic. And that's what the prior looks like. So it's functions that wobble up and down in a square exponential kind of way, but globally they look like polynomials. So they're non-stationary. They can go to very large values. What this allows you to do is to get models that capture the fact that this function kind of moves up in this direction, and it also moves up in this direction, which is something that a stationary kernel could not represent. It's also, from a scientific perspective, if you're using this to model the real world, an interesting way of combining finite dimensional representations, which are good because you can talk about them, with the power of a non-parametric representation, which is good because you have lots of flexibility. So this is a model that would say, well, what I'm looking for is a polynomial quadratic behavior with a little bit of local variation, which is something that I maybe don't care so much about, but I want it to be modeled well by the algorithm. By the way, this sum property can be used in very elegant ways to build to generalize these regression models to high-dimensional settings. So this is a Gaussian process prior over two-dimensional input domain with a general square exponential covariance, or a product of two square exponential functions. And it's a relatively wild sort of general model, which is harder to learn than just two linear problems, because the volume of this space is quadratically larger than the volume of a one-dimensional input domain. Instead, you could sum two independent functions, one of which only depending on the first direction, the other one only depending on the second direction. And what you get is what's called an additive model, which is much more restrictive, but also learns much more quickly. So if you think that your function, that various inputs to your functional problem actually have independent effects on the function output, or separate effects, then this is a way of kind of constructing this. This is sometimes, finding these kernels is sometimes called functional ANOVA. This is a much older idea actually, which has been around sort of in the kernel regression community, at least since 1990 when Grace Baba wrote about it. As a final property, which is much less obvious than the other previous ones, and that is if you pointwise multiply kernel functions. So that's what in MATLAB is called dot star, or which I think in Python that's just the actual times, right? So if you just multiply two matrices by just multiplying the elements, then you also get out a positive semi-definite matrix if both of the inputs are positive semi-definite. It's completely not obvious why this is the case. It's a theorem that was initially proved by Isai Shur. You can find proofs in the sort of more modern literature as well. And what it allows you to do is notice that the product of two numbers is small if either of those two numbers is small. So you can use this to encode some kind of AND relationship in terms of similarity. So these two function values on this domain are almost independent or weakly related to each other if they seem to be weakly related under either of the two kernels. So in this case, again, square exponential kernel and a 3 degree of freedom polynomial model, and this is what the posterior looks like. It's a much more liberal, sort of weak model than the AND summation model previously. So here are these four properties taken together again. We can multiply the output of a kernel. We can scale in a nonlinear way even the input of a kernel. We can add and multiply kernels to get out new kernels or covariance functions. This is just one sort of set of observations about the algebraic structure of the space of kernels. It doesn't tell us much about the size of the space of kernels or where we have to search for them. We could just start with certain kernels and just sort of try and build new ones using these operations. If you use these models for regression, though, it's adding a lot of headache to your sort of philosophical argument, because the space of models is so large, and you've just noticed in these plots that choosing these kernels has a radical effect on how these models regress, what kind of functions they learn. There are certain aspects of the function where almost all of these kernels do very similar things if they are reasonably sanely chosen. There are other aspects where they differ wildly. Interesting aspects, for example, are extrapolation. The extrapolation behavior of these different models are very different. The interpolation is sometimes a little bit easier. Other aspects are differentiability, computational cost of these models, because in some cases these covariance matrices have a structure which makes it easier to deal with them. So in the final 15 minutes, I'll like to do sort of something slightly cautionary, which I've sort of already hinted at with what I just said, but I want to make it slightly more explicit. So this is going to be a little bit difficult, because to really get this right, to make a sort of a vigorous argument about this, I would have to go into great detail about the structure of producing kernel Hilbert spaces and the relationship between GPs and RKHSs. I can't do this in 15 minutes, so instead I'll just give you a little observation, something to sort of think about when you choose these models. So a kind of argument that you could have had, that we could have gone through so far is, well, we want to use these algorithms because they're algebraically nice. Right? They allow us to do very nice, elegant machine learning just by using linear algebra. We've noticed that we can choose these languages. We have this big choice of language to describe functional relationships. It involves all these different feature functions, and we have to choose all these feature functions. And if you use only finitely many features, that's like using a language that has only finitely many words. In this case, like only maybe 18 or 20 or 12 words. So it's very restrictive if you're trying to describe functional relationships between input and output. Now, what this non-parametric limit seems to give us is a more universal language, a language with infinitely many words, infinitely many features. So that sounds very powerful, and it could sort of raise the hope that these models might be universal models that you can use to learn any function arbitrarily well. Just like we can use natural language to describe everything we can talk about as humans in a sort of general way. And now you might wonder about to which degree this is true. So how powerful are these methods? Are they really regression algorithms that allow us to learn everything? Or is there still something going on that sort of restricts this class? And a cautionary observation we already made was, when we went through this sort of this algebraic structure of this space, is that we observed that there are all these different kernels, and they react in a very different way to a particular data set. So if we use these different languages to describe sort of what we learn about the function when we observe data points, then these different languages will give us different answers to what the regression answer is, essentially. So after finitely many data points, we already know that this space might be universal, but it's not unique. There is no just one kernel which allows us to do the correct regression. We have to be careful. We have to choose hyperparameters. We have to choose the structure of the kernels to get a good regression model. But what happens if we have very large number of data points? Do we eventually all converge to the same kind of thing? Well, it turns out that this kind of question was asked maybe outside of the Gaussian process community by a different community in machine learning that Niels already mentioned, the kernel regression community. by people like Berat Shirkov and before him Vladimir Vapnik and Alex Smola and people in this form, and much earlier even by Grace Waba and colleagues, on what is the sort of the space of functions that you can cover with these regression algorithms. And an important concept in this sort of under this aspect is the reproducing kernel Hilbert space, which, as I said, I have to be very hand-wavy about because there's not enough time to present it properly. And what this essentially is the space of all functions that can be a mean function of a GP. So if you look at what the mean function looks like, it's this data point that you observed. I'm assuming zero mean here. Data point you observed scaled by the prior covariance times this map between observed points where we observed and points where we're predicting. Now you can just multiply those two things because they both depend just on the data and just call this a vector. This is a vector mapped through a matrix, so it's just a vector. You could call this the weight vector alpha. And then what's left is just this function here. This is a matrix which contains kernel values. And if you only evaluate this thing, this prediction at one point x, then what this essentially gives us is it takes the kernel evaluated centered on each input location. So these are these gray functions scaled by the elements of this vector alpha. This is why these functions point in different directions. And out comes this fat red line in the middle, which is this mean function. This is, by the way, also the least squares estimator, so it's closely related to things that people use in other areas of statistics and machine learning. Now you could wonder, what is the space of all functions that I can represent with that's sort of covered, that I can reach with this red lines, red thick lines like this that have been described in this particular way. This space under some normalizability properties is called the reproducing kernel Hilbert space. Now for some kernels, do I have a, no. So there's some kernels, the square exponential radial basis kernel is one of them, but there are several other ones, which have an intriguing property, and that is that this RKHS, this space, lies dense in the space of all continuous functions over some input domain. So it lies dense in a similar way to how the rational numbers lie dense in the space of real numbers. So it means that if you have any odd function that's continuous and that you might be interested in, then for any epsilon that you allow yourself to be wrong, and this might be an arbitrarily small epsilon, there is a function in this RKHS which is at this distance under some norm to the function we're trying to learn. So this non-parametric model gives us a language with which we can address any continuous function in an arbitrarily good way, where we can get arbitrarily close to. That sounds extremely powerful, right? That means these models are a lot more powerful than these parametric models because they allow us to get arbitrarily close to any function we might be interested in. Now, notice though that that's not a statement about how many data points you need. It's only a statement about whether this kind of description can reach certain functions. Now what you might want to ask is, how large does this n have to be to get arbitrarily close? What's the functional relationship between how close I am to the thing I'm trying to learn and the number of data points I have to collect? Well, instead of doing complicated theorems, let's just do an experiment. Here is, in green in the background, our by now favorite radial basis function square exponential Gaussian process. I'm not drawing samples now to make it slightly less sort of confusing. This is the thing in the background. It's a square exponential prior with standard deviation 1, so standard deviation, and length scale 1. This blue line here is also a draw from a Gaussian process. It's from a different Gaussian process. It's a Gaussian process also with zero mean with a rational quadratic covariance function. So that's an ever so slightly different covariance function. If we had more time to talk about the structure of these spaces, I could go on about how similar the square exponential and the rational quadratic are to each other. For example, they have the same eigenfunction. Doesn't really matter, but they are very, very similar. They're very closely related models. So they are not, I'm not trying to sort of set up a difficult problem here. It's the same, this process also has the same standard deviation output and the same length scale. So essentially all the parameters are right, just that in the space of kernels there's an ever so slight difference between the process that generated this blue line and the process we're using to learn it. Let's see what happens if we try to learn this function. I get my first data point, my first observation over here. I'm going to draw these evaluation points uniformly at random on this -8 to +8 space. because that's usually what these convergence proofs assume. After I get the first observation, everything is fine. My prior begins to converge. I get more. Now I have a second observation. Now I have 5 observations. Everything looks reasonably nice. The posterior uncertainty covers the regions in which the true function lies. So this is a meaningful regression model. Now I have 10 evaluations. This looks all really well. We're converging nicely, which is not surprising because this is a universal kernel. We can learn any function. Now we get 20 points, and everything just blew up in our face. This looks really bad, no? So if this is your regression problem, you've just screwed up completely. This is a really bad prediction over here, right? Now, well, it doesn't really matter. The theorem only says we can eventually get arbitrarily close. So let's see what happens if we just get more points. Here are 50. Ooh, it gets worse. Now, by the way, this space goes from -8 to +8. So there are 16 sort of volume elements in here. And the length scale of this prior is 1. So we have essentially 16 degrees of freedom in this model for reasons that I'm sort of slightly glossing over. And we already have much more than the degrees of freedom data points. So this is already really well covered as a space. It should already have converged pretty well. And imagine if this were a 50-dimensional regression problem, how hard it would be to cover this space really well. Right? This is our volume 60, and we've already covered like more than 2 times over. Here's 100, it gets even worse. 500, okay, now we're sort of getting close, but what you don't see is these horrible oscillations in between. But at the data points, we're actually getting closer and closer. What you also don't see is what happens on the left and right. It's horrible. This thing blows up to like several thousand in prediction, and then comes down in a really wide, smooth arc over here. If you continue this experiment, you can do something like this. So what I did here is I took exactly this thing that I'm plotting here. I'm also holding out, without showing you, 10,000 test points, which are also on this domain, and they are on a regular grid. But they are not the evaluation points. And I'm evaluating on this predictive mean the distance between the test points and the predicted points. This is what this red line tells you as a function of the number of function evaluations. This is a log plot. So there's a lot of stuff going on here. And this red line tells you this error that we just saw. So this was the region where things blew up really badly, around 10, 20, 50. And eventually we get closer again. But notice that this line does not become a straight line eventually that just falls sort of at this rate. This green line here is a decay of order square root number of data points. So it's sort of the optimal statistical regressor convergence. What it looks a lot more like is this yellow line, and that's a logarithmic convergence. In fact, it turns out there's actually a theorem which was published in 2011 by Art van der Vaart and Jan van Zanten, which says that for this particular choice of rational quadratic and square exponential kernel, which are sort of a good example for 2 models that are very close to each other, this convergence is actually logarithmic. So to lower your error by a certain factor, you have to take an exponentially larger number of data points. So what's happened here is, what the sort of takeaway from this message is, what these models do is they give you a universal language to describe everything, any possible function you might be interested in. But this language is such that certain words in this language, certain models, certain functions, certain objects you're trying to describe, require exponentially longer words, exponentially more data points than other functions. Yes?
Sorry, is that scale in the dimensionality as well?
So in the dimensionality, there's another completely separate problem, that just the space of these functions you're trying to address just exponentially grows in the number of dimensions that you're addressing. So that's completely separate from it. It's also horrible, but even in 1D, it's hard enough. So for those of you who find this a little confusing, here is a maybe slightly weird comparison. I'm not sure whether this helps many people, but for some of you it might be helpful. Here's a comparison to a completely different problem. Notice that I'm using the word dense, lying dense in some space. A good example for something that lies dense in some other space is the rational numbers. Those lie dense in the space of real numbers. So here's an example of sort of a similar situation in sort of basic mathematics. Let's say you don't know about pi, the circle number, right? The pi, just pi, the thing for which we don't have any other name. And I have to tell you about pi. So I need to convey information to you via the channel of our numerical language about what the value of pi is. Now pi is an irrational number, so it does not lie in the space Q. But the numbers we use to describe stuff, describe numbers, are rational numbers. I can't write real numbers. Right? I can only write rational numbers. So one way to do this would be to use the language of decimal expansions. And then I could give you sort of data points in a particular basis set. And if I'm sort of in this classic Arabo-Western culture, then I might use this sort of decimal number basis set. So I'd use the basis 1, 1/10, 100, 1,000, and so on. You can think of these as feature functions. And I give you weights for the individual feature functions. The first weight is 3, 1, 4, 1, and there's someone in the room here who knows them up to 200. Right? Now, imagine you get to talk to, I don't know, some member of some long-lost culture somewhere in the Southern Pacific who use a different algebraic way of talking about numbers. They don't use decimal numbers, they use fractions, and they count in fractions. So they use 1/1, 1/2, 1/3, 1/4, 1/5, 1/6, and so on. That's also a universal language for Q. And actually, if you've done a basic undergraduate math course, you may have heard that Q is countable in exactly this kind of way. So let's say that's our basis for the rational numbers. Then I could also try and convey pi to you, and it would be a particular natural thing to do, because you can write pi in this basis as +4, 0, -4, 0, +4, 0, -4, 0, and so on. This is called the Gregory-Leibniz series expansion. However, if I did this, if I used this feature set instead of this feature set, this kernel instead of this kernel, if you like, then the rate at which I get closer to the true pi is logarithmic. It's very slow. And I need lots and lots of terms to get close. While in decimal numbers, of course, I'm converging sort of linearly in an exponential space, just because this basis sort of has precision that increases with the exponential. There are even other languages which people have custom designed just to represent pi. These are these people who built these algorithms to get arbitrarily high precision descriptions of pi. There's a series expansion called the Chudnovsky rule, which was written by two brothers, the Chudnovsky brothers, who are sort of the world champions in expanding pi. And it converges radically fast. So fast that I can only show you one data point, because after the second data point, it's outside of the floating point range. So I can't talk about it anymore. Now, mentally, something to keep in your head is, what we're doing in machine learning is we're trying to find words for the entire world, right? Describing everything you might be interested in. And the eternal problem in this domain is that you have to strike a balance between specialized languages which work very well on particular problems and universal languages which don't work so well on everything, which work sort of reasonably well on almost everything or on very interesting large spaces, but are sort of not necessarily so good on a very specific problem. Gaussian processes in this, on this domain, sort of on this description of the problem space, are very interesting because they cover the entire range. If you know that the function you're describing is very simple and can be described in 1 or 2 or 3 numbers, like a linear function, then you can build a model that converges extremely fast if the model you're trying to learn is actually a linear function. If the true function is not linear at all, then you've just really screwed yourself over, right? Because you can get an arbitrarily bad description. If you use a non-parametric description, like a square exponential kernel, for example, you now have a language which covers the space of all continuous functions, but it covers certain functions in a much sort of less dense way than other regions of this function domain, where the representer points sort of lie a lot closer, a lot denser to each other. So to get a model that works well on your particular data set, you have to think about where this prior model puts density over the function space. And one way of thinking about this, in a very naive way, are those plots that I showed you. So of just drawing from the prior, checking what the properties of these functions are, and thinking about whether they match what you're looking for. However, sometimes this can give you very sort of the properties that makes things converge or not converge well can be very sort of non-obvious. As in this case, where we have a prior that actually sort of looks reasonably well. So if I would draw functions from this prior, they would actually look a lot like this blue line. But there is something about this blue line that makes it very hard to learn this function. And Seymour and other people can tell you more about this. It's something about the Fourier spectrum of this prior, in this particular case. But if you had another regression problem, there might be something else. It might be something about the Laplace spectrum also.
So if you did it the other way around, though, things would be much better, wouldn't they?
Yes, but then of course you could find another example of something that doesn't work well with
It's
the
an important point, isn't it? Because we're always using it as exponentiated quadratic, yet we know that this function is much quicker to approximate the exponentiated quadratic than the exponentiated quadratic is to approximate this function, which already immediately should indicate to us that maybe this is a better function, a better covariance function to use.
So the square exponential is, in some technical sense, a corner case of the space of stationary covariance functions. I don't know the full background to this. Maybe Nicolas can tell you more about this. It's something about sort of, it's actually sort of a dangerous thing to do because these draws from the square exponential are infinitely often differentiable, and they have an exponentially decaying Fourier tail in the frequency domain. So they're really sort of a dangerous object to work with. The main reason why many of us use square exponential kernels, and you can't blame us for it, well, who knows, is that because they are these Gaussian functions, you can sort of, after you've done regression, you can do lots of cool things afterwards because you can integrate this kernel just in the same way that you can integrate Gaussians, and you can differentiate it, you can multiply it with other things. It's a nice function to work with. It's just algebraically convenient. But from a modeling perspective, it's a little bit dangerous. With that, I would like to come to a conclusion. Here is my summary. So the main story was Gaussian distributions are the link between linear algebra and inference, because if you have a bunch of variables which are jointly Gaussian distributed and you only make linear or affine observations, you stay within the confines of the Gaussian language doing inference. We can use the Gaussian framework to perform regression, to learn functional relationships between x and y, and the way we do that is we design languages to describe functional spaces in such a way that there is a linear part of the description over which we can do Gaussian inference, and a nonlinear part which we just fix, just so. We just claim that it's the right one. And then we might want to optimize it afterwards, and that's a nonlinear problem. In fact, there's a very nice algebraic observation that we can even build models that have infinite degrees of freedom, infinitely many features. And these are called Gaussian process, non-parametric regression models. And in fact, there is an entire space of them. In particular, you can take these covariance functions, which parameterize these objects. So the prior mean, I agree with Neil, is not important because you can just add any prior mean you like, and it's still a Gaussian process. It can be any function, non-differentiable, not even discontinuous, doesn't matter. The covariances are the important bits, and we observed that the space of these covariance functions has quite a rich algebraic structure. We can scale the outputs of a kernel, we can scale the inputs of a kernel and retain Gaussian process properties. We can add and multiply pointwise these kernel functions, covariance functions, to get Gaussian process models. This allows us to build very expressive regression models, and it's a powerful property, but it's also philosophically sort of, it sort of dampens the excitement you might have about these models just after observing that they exist. Because you just notice that it's almost as hard finding a good kernel as it was hard finding a good feature set. And in fact, we can combine parametric models and non-parametric models to get even more expressive models. So the choice of kernel function has not really been taken from us, but there's a little bit of solace, and that is that there is actually something about these non-parametric models. And it's the fact that they cover the space of functions you might be interested in a nice kind of infinitely flexible kind of way. So they actually are more powerful than parametric regression models, but they are not arbitrarily powerful. They can get arbitrarily close to any function, some of them can, any continuous function, but they get arbitrarily close to some functions exponentially faster than they get to other functions. So this is a very powerful model that's very, very much worth investigating and using, but it's also no panacea. All right. With that, thank you very much. Let's see whether I get to use my big backup. Yes?
You showed us this example where an intuitively appealing kernel did a bad job.
Yeah.
In general, should we avoid intuition?
No. I would it's completely the other way around. I think you should use intuition, but it's worth we're still in a phase where we're still, I would say, early on beginning to understand how these models really work. So the fact that this theorem that I've quoted here is from 2011 gives you an indication of how early on we are in understanding these models. So we will continue to understand more and more as we all in this room work on these models. And as we do, I think the right thing to do is to just keep up with the literature as much as you can, and sort of keep a feeling that these observations give us more and more powerful ways of thinking about these models. So intuition is right, but you have to have intuition about something, right? And a simple form of intuition is this length scale kind of intuition that I can draw from this prior. Let's go back to some of the earlier examples. This kind of thing, right? I can draw from this stuff. I can look at what the draws look like. And this gives you a good feeling already for what kind of model you're building. And it's covering lots and lots of aspects like the ones that I talked about here. And if you're only sort of typically in a realistic regression problem, you only have a very small data set compared to how many things you're trying to learn, right? Neil will, of course, point out again that if you think that you're already in convergence, if you have a lot more data points and you have degrees of freedom in your model, you're just using the wrong model. You should just use a more powerful model, probably, right? So in that region, in that domain of the convergence sort of behavior, it's very much worth doing doing plots like this. Of course, it's sometimes quite hard to do this because usually you don't have one-dimensional input domains. But you can still try and do that, and that helps a lot building good models. At the same time, there are sometimes tricky bits that you just have to know about the mathematics of them. So for example, in this particular example that I made here, if you would look at this function in the Fourier domain, you would notice that it's a very bad fit, because it would look very different. In the Fourier domain, the weights of this function have a rationally decaying tail, so they are very heavy-tailed, while the weights of draws from this prior have a Gaussian tail. They decay very quickly. And you will hear more about this from Simon, I'm pretty sure.
Am I right in thinking then that regardless of the underlying function you're trying to model, the posterior mean is always going to be continuous?
No. So, where do I have my example with the step functions? So you could have a prior mean, which if you use these parametric descriptions, then you can actually just get steps. So too many slides. Here we go. This is a model that gives you a non-discontinuous posterior mean. And so there's an interesting question here of to which degree you can generalize this to a non-parametric formulation with a GP.
Okay.
So if you do this limit, this limit of this is the Wiener process, and the Wiener process can model functions which are discontinuous, but only in a very awkward kind of way, because draws from the Wiener prior are actually always continuous, or almost always continuous. It's just that if you have two data points which are arbitrarily close to each other and have a step, then it sort of actually makes this step. It's able to do this step, but a draw from the prior would never do that. If you want to have a model that has a discrete step, a finite number of discrete steps, then you would use a feature model like this with parametric features, and then you might optimize where you put these steps. That's a way of doing change point detection or step detection, or you might even have a mixture model over them, and there's lots of work on this sort of in the early 2000s actually. Zubin and Karl did some stuff on infinite mixtures of Gaussian process models.
Okay.
No more questions.
So, I mean, one of the things, a lot of you will have really understood this and stuff about the importance of the prior, because you'll have already read our Latin motto from the summer school, which is on your shirts. So, one of your tasks is that the great thing about having a Latin motto is there's uncertainty about what it means, because none of us actually speak Latin. So, one of the interpretations of what it's saying is that the posterior is the student of the prior, which is a distortion of today is the master of tomorrow, or the prior is the master of the posterior. And I think that's really, really important when you're doing any Bayesian inference. And I think Philipp has done a really good job of displaying that. Could you just put 62 up again? I really like
62.
62. It relates to sort of what I was saying. So when I sort of made this point about I love linear regression models if I've only observed one data point, and Philipp was sort of saying go a bit forward to just before it all goes wrong. So I don't know, was it 10 data points? See, this is great. At this point, you're sort of happy marginally. You're not actually happy with your joint correlations because you won't capture this, but you're marginally happy with your predictions because you haven't seen enough data to expose the flaw in your prior. Right? Just as in the linear regression case, when you observe one data point, you haven't yet observed enough data. So marginally, the predictions look good. The correlated predictions do not look good. What happens when Philipp adds more data here is actually you start to see points which expose that the smoothness of the underlying prior is different from your smoothness assumption. This exponentiated quadratic assumes infinite smoothness, yet this thing is not infinitely smooth. So you get this sudden mismatch. You sort of expose the flaw in your model.
It is actually. It's infinitely smooth. It's a rational quadratic flaw. So it's
no, the rational quadratic is it's got a roughness. It's got many length scales. Sorry, I'm confusing between the term. So it's a rational quadratic, yes, but it's got many different length scales. It's a sort of infinite sum of length scales. An infinite sum of these are RBS. So what you then see, what suddenly appears is, there's something else going on at a different length scale. The length scale is shorter than I thought before, so it all just, it messes everything up and exposes the flaw, which is similar to the sort of case when you've observed 2 points. So actually, there's enough information now, I guess, for it to really be confident about what's going on, but it's incorrect. And that's where you get this problem. So often as data increases, you tend to get these issues occurring. And this covariance function is particularly bad when you start seeing data very close together because it really exposes the flaws in that. And the response, as Philipp said, that I would say, and a lot of people would say, is to try and increase the complexity of your covariance function to model better. I think that's a really nice example of what can go wrong. So if we could just thank Philipp again for a great talk. And Philipp will return to talk about Bayesian numerics. So we're going to have lunch now, and after lunch, I think scheduled to start is at 1:30. Sorry, 1:15. We're going to start the lab session. Now, the lab session we feel is quite important, but it is kind of difficult. It's all scheduled to run in IPy